Okay, you should have your new notes packet in front of you, and we're going to cover topic 1.2 carbon and sort of the neat molecules that carbon can make in this video. So let's start with kind of an intro. Now, this is not something that you're writing on your notes. This just gives you a little bit of perspective as to why in the world we're even talking about this. So, approximately 96% of all living things are made up of these six elements. And so you have carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And so if you start mixing these up in various combinations, building more complex and more complex molecules, you get pretty much the molecular basis for life. And so as we start to talk about building these complex molecules and working our way up towards a cell, which is the smallest unit of life, we're going to talk about carbon specifically. Now, we'll see some of these other elements at play, but carbon is pretty unique. Now, you know that bonding, if we're going to put together a molecule, we're going to have to form some bonds within that molecule. And bonding is based entirely, not entirely, but bonding is based in large part on valence electrons of the atoms. And so here are a few of those six basic elements of life. Here is hydrogen. Notice it has one valence electron. Here is oxygen. It has one, two, four, six valence electron. It's looking to pick up two additional. Here is nitrogen that has five valence electrons, is looking to pick up three additional or bond to three additional. And here's carbon that has four. And so carbon is interested in bonding with or creating bonds with four additional electrons or four electrons from additional atoms. And so we're going to talk specifically about carbon today. And we'll start first with the idea that carbon is tetravalent. And so here's a nice little picture of something that is tetravalent. It has four valence electrons, which means it can form up to four covalent bonds. So tetra as a prefix means four here. Now that allows for carbon to create some really big, complex molecules that we will call macromolecules. There are four main categories of macromolecules: lipids, nucleic acids, carbohydrates, and proteins. And all of these, if you kind of zoomed into their molecular structure, you're going to find lots and lots of carbons embedded in their molecular structure. So this carbon chain right here helps us to see that each carbon is tetravalent in that it bonds to four, one bond, two bond, three bond, four bond neighboring atoms. Here you can find a central carbon that is tetravalent, one, two, three, four bonds, always four of these lines coming off of a carbon. Even if you look at this carbon right here, there are still four lines coming off of that carbon. Two of them are in a pair, and we'll talk about what that means in just a second. But here's the third and also the fourth. So because carbon has four valence electrons and can form four bonds, we can make some really cool large molecules. Next section of your notes, carbon can form single, double, or triple bonds. And so let's look at this image up here at the top. This shows us a single bond illustrated by one little stick. The stick is a bond line. Here's a double bond, looks like an equal sign, two lines, and here's a triple bond. Notice that there are never any more than four lines total coming off of any carbon. So off of this carbon, there's one, two, three, four. Coming off of this carbon, one, two, three, four. Same thing over here. Each of these three plus their outer bond gives us 4. So they can form single, double, and triple bonds. They can form structures that are called chains, branched chains, or rings. And so here we see that illustrated. So here is a straight chain carbon. So here are all of the carbons in a line. Here's a branch chain carbon. And here is a ring of carbons. Another cool thing that carbons can form are hydrocarbon chains. So these are specifically carbon chains that have hydrogens off to the side. And so here's where you can see the bonds. This is a different kind of model of that same molecule, except this one has an additional grouping here on the end. But what's cool about hydrocarbon chains, hydrogen and carbon have nearly the same electronegativity values. So that means when they start to share their electrons, they share them equally within the bond. So hydrocarbon chains are nonpolar, and we know from previous conversations about water that nonpolar molecules are also hydrophobic. So hydrocarbon chains are really the basis of our fats and oils and waxes that are nonpolar. Next section of our notes, the concept of isomers. We're not going to get too far down in the rabbit hole here because you're going to talk about it in chemistry. But an isomer is illustrated up here. So if I were to talk about this molecular structure right here, this molecular structure, there are 2 carbons, there are 6 hydrogens, and there's 1 oxygen. Well, we write that as a molecular formula. And so here's that molecular formula, C2H6O. That tells me that there are 2 carbons, 6 hydrogens, and 1 oxygen. Isomers are molecules that have the same molecular formula, but the actual arrangement of the atoms in the structure can be different. And so same molecular formula, but different structure. This is an example. So here, these are both molecular formulas C2H6O, but notice this configuration of C2H6O gives us ethanol, and this configuration of C2H6O gives us an ether. So isomers are molecules that, again, have the same molecular formula, but the atoms within the molecule are arranged differently, and so we see different structures. Now, there are also isomers that are special called enantiomers, and that is a very odd word, but some of these isomers are enantiomers. Enantiomers mean that they are mirror images of each other, sort of like if you hold both of your hands out in front of you, palms facing up, your hands are mirror images of each other. And so here is an example. These 2 molecules are mirror images of each other. Both are ibuprofen, which is what is in Advil. And so this form is called S-ibuprofen. This form, the mirror image, is called R-ibuprofen. What is interesting is that one of these forms is active and works like Advil does for a pain reducer and also to reduce inflammation, but the other does not. And so even though they look pretty similar, they actually are very different. One is effective or active and the other is ineffective. Here's another example. These 2 are albuterol. Albuterol is what it treats, it's a treatment for asthma, but many of you might have an inhaler or you might have done a nebulizer at some point in your life. Albuterol is most likely in your inhaler and a part of what you're putting in your nebulizer. It's going to open up your lungs when they feel really tight. And so this is R-albuterol. The mirror image is S-albuterol. It turns out, even though they look the same, this is the only one that actually functions like it should in your body as an asthma medication. And so this is another great example I've highlighted over here. Structure determines function. So the shape of these molecules really does determine what they are able to do. Last little section here, let's talk about functional groups. So, functional groups are these sort of collections of molecules that are attached to a main carbon skeleton. And so, this is a great example. These four rings over here, that is sort of, think of that as like the base structure of this molecule. And so, they share that in common. They both have these four yellow rings. But then look up here, there's an OH. There's something called a CH3, there's another CH3, and there's a double bond out here to an oxygen. This one's a little bit different. We still have the OH, we still have the CH3. We're completely missing the CH3 that is right here. And instead of a double bond to an oxygen, we have a single bond to an oxygen and a hydrogen. So this is a great example of functional groups. These little things that are in blue, they're called functional groups. They are groups of molecules that are attached to the main carbon skeleton. And even though the majority of the molecule looks the same, the different functional groups really make these molecules two very different things. And so this one is estradiol, which is the basis for estrogen. And then this one is testosterone. And I'm sure that you have perhaps heard of estrogen in females and testosterone in males, and how they really do function very differently in the development of primary and secondary sexual characteristics. And so just a tiny little change of these side functional groups changes the overall structure of the molecule. So again, another great example of how structure determines function. Now, in our biochemistry conversation for AP Bio, there are a couple of repeating functional groups that we're going to talk about very, very, very briefly. We actually don't have to know as much now as we used to for the AP test about functional groups, but I do want to touch on a few of these. So we're going to look at something called a hydroxyl group. We're going to look at an amino group, a sulfhydryl, and a phosphate group, and one that is not pictured, which is called a methyl group. So here are those popular functional groups. We'll start with a methyl group. Methyl is a hydrocarbon. So it is carbon bound to four hydrocarbons, sometimes four hydrogen. Sometimes it's only bound to three hydrogen because the carbon has to have a bond free to fit into a larger carbon skeleton. But if you see CH4 or CH3, that is a methyl functional group. Anywhere you see that, you're going to need to associate properties of fats with that. So the non-polar aspect, methyl groups make molecules non-polar. Then you have hydroxyls, OHs, and we have talked about hydroxyls when we've talked about pHs and sort of where hydrogen ions and hydroxyls exist on the pH scale. Hydroxyls, we find a lot of those on sugars. And so hydroxyls will help to make a substance soluble and dissolve into water. The amino group, I point this out because we talk about amino acids. The amino group is an NH4 or an NH. It could be NH2, 3, or 4. And notice that it has nitrogen in it, which is sort of a new thing. We haven't seen that with our previous functional groups. And we find these in the backbone of the building blocks that make up proteins. Those building blocks are amino acids. Then there's a phosphorus group, PO4, PO3. These are found in all of our bases in DNA and in RNA. So these are found in nucleic acids. And notice it has phosphorus as well, which is kind of a unique thing. It's not in all functional groups. Last but not least, sulfhydryl, sulfur and hydrogen bound to each other. We find these in proteins and in other molecules, but specifically related to proteins. So we need to be able to kind of recognize when functional groups are attached. We need to be able to recognize what functional groups are in the lipids and the carbohydrates and the proteins that we're getting ready to study. And then we also need to be able to recognize here in this, we started with a slide that said 96% of life is made of carbon, hydrogen, oxygen, sulfur, phosphorus, and nitrogen. And here we see all of those. So the next topic will be topic 1.3, and that is coming in a different video. So you are done.